Welcome to the demo of our two-link robot. Our robot is constructed according to the principles of Soft Subdivision Search. It is an example of what we call a resolution exact algorithm. We'll begin in the directory of the core library for our two-link robot. I'll begin by listing the files in this directory. Here you see that this executable two links is the name of our precompiled robot, and there's a make file here which encodes the various parameters for running examples and compiling the program. To find what examples are possible, let's type make help, and it basically tells you that you can type make to compile the program and make EG to run a default example, and there's a list of various examples from EG1, EG2 to EG300. Let us look at what EG2 gives us. This example shows our robot navigating in an environment with 8 corridors. To see this environment more clearly, let us click on Initial Configurations, and you see that there are several triangles which serves as obstacles, and to see them clearly, let's shade the obstacles. So now you see the triangles shaded, and they leave a set of 8 corridors which converge onto a central area. And our robot is a two-link robot, and the links are colored black and red. And the initial configuration of the robot is indicated by this double circle in cyan color, and the final configuration is inside this magenta circle. And notice that in the central area there are 3 tiny obstacles as well. Let's rerun the animation. What we see in this animation is that the origin of the robot, which is the point about which both links rotate, traces this blue curve on the screen from the initial origin to the final origin. Let's see what the various color coded boxes mean. I will turn off the shading. First of all, you see that there are yellow boxes. I'll click on one of them, and in this output area you will see that some information about this box is given. It tells us that the box is mixed, and it gives us the x and y coordinates of the center of the box, and the width of the box is 128. Let's click on one of these green boxes. It says again that the box is mixed, except that this time it gives us various angular ranges. It has 4 angular ranges here. 2 of them corresponds to the link L1, and the other 2 corresponds to the link L2. So L1 link has a range from 141 degrees to 156 degrees, and another range from 331 degrees to about 1.4 degrees. So 331 to 1.4 wraps around 0, because this is an circular angular range. And these 2 ranges correspond to the position of the first link with its origin placed in this blue box, and where it's constrained by this wall up above the corridor and this wall the lower side of the corridor. And clearly these 2 walls together constrain link 1 to 2 angular ranges, which are just what we have seen. Now if you look at the angular range for L2, they're pretty close to the ranges for L1, and the reason is our link lengths are about the same. L1 has length 85 and L2 has length 80. So we expect the range to be rather similar. And of course the final color, red, corresponds to the status of being stuck, which means that the robot in this any configuration in this box will be a stuck configuration. If you can see very closely, there are also some gray boxes. I'll try to choose one of these gray boxes. Yes. The gray box is basically a mixed box whose width has reached the minimum epsilon below which we will not split. So you see here that this width is 4. And 4 is the minimum because we have set epsilon to be 4 in this input. Let's go on to the next part of this demo, which is to look at the various search strategies. The first run that we had is based on strategy number 2, as we said, and that's the greedy heuristic. And now let's try the random heuristic. I click that and I click run. So you see here that the random heuristic has split all over the place, unlike the greedy heuristic. And if you look at the output from this run, which is run number 2, it says that a path has been found. The time is 1034 milliseconds, which is a bit more than the previous 774 milliseconds. But the number of steps is 49,304. That's more than double the total number of steps in the first run. Generally, we find that step counting is more reliable than the time because it does not depend on the states of the CPU and other processes that might be running in the background. So since this is a random heuristic, we can run it again to get a different set of results. And this time we see that it looks like there are more unsplit boxes, like this big yellow box is not split and so on. And if we look at the time used, it's somewhat faster than the first run, but that, as we said, is unreliable. If you look at the total number of steps, it is indeed there are fewer boxes. It has about 42,000 boxes as opposed to 49,000. Let's try the next strategy, breadth first search. And as the name suggests, we split bigger boxes before we split smaller ones. So let's run it. And you can see now the splitting is fairly uniform. It's sort of split all over the place. And it found a path. And if you look at the run statistics, it is even slower than the random run. The number of steps is 53,000 as opposed to 41,000 or 49,000 in the previous 2 random runs. Let's try the next strategy. Well, we have seen greedy, so we won't run it again. Let's go to distance plus size. This is basically a mixed strategy alternating between the greedy method and the breadth first search method. Let's run this. And now we see that if you look at the boxes that are split, apparently fewer boxes are split here than even the very first strategy, the greedy strategy. And if you look at the numbers, this is run number 5. Indeed, the time is pretty good, 551 milliseconds, and the number of boxes is 21,400, which we can compare with the very first run. The very first run had 23,800 boxes. So indeed, this is the best of all the strategies we have seen so far. So with this, I will quit. And I would like to show just very quickly several other demos. One of the strengths of our resolution exact algorithms is the ability to report no path. So I'm going to do an example called the bug trap. And the bug trap, and we look at the initial configuration, looks like this. So the initial configuration is inside the trap, and we want to reach a configuration outside the trap. And to do so, it has to navigate through this narrow passage. And as we see in this run, it reports no path. And it takes about 3,500 steps to find this. Now, the reason it found no path is that we have set the epsilon to be 5. And basically, while trying to get out of this narrow passage, it got stuck around this part here. But suppose we were to change the epsilon to 4 and run it again. And this time, it found the path out of the bug trap. Just very quickly, let me show two other examples. Make e.g. So this is an interesting example of a robot moving in a two-chamber environment, and it has to configure itself to the final position by going around the chambers. And one final example, make e.g. 300. In this example here, the robot is navigating in an environment with 300 randomly generated triangles. And to show the free space more clearly, I'll turn on shading of obstacles, and you can see that it is moving in some pretty tight environments. Well, thank you very much for your attention, and we hope you will download our core library to test it out for yourself. It's available at http://cs.nyu.edu/exact. Look for core library and downloads. Thank you.